Yeah. Minute is fine. Oh. That's live. Oops, go ahead. Go ahead.
All right, everyone, if you can please get seated as quickly as possible. We're about to get started momentarily. In fact, we're about to get started right now. I changed my mind. So my name is Yi-Sung Yu. I'll be chairing this tutorial session. It is my great pleasure to introduce Ben Reck, and I'll keep this brief so that he can get going. Ben is on the faculty at EECS at Berkeley. He's done a range of research on a range of topics, most recently at the intersection of learning and control, which is what he'll be talking about today. Just one quick logistical note. If you have a question during the Q&A session of this tutorial, please ask it at the mics that have been set up for Q&A so that it will get recorded. And with that, let's welcome Ben Reck.
Hey, hey. Oh, this is on? Great. Welcome to Stockholm, everybody. So where to begin? Today is a kind of a culmination of, I guess, what was a 6-month-long project. We're trying to write up some thoughts about reinforcement learning, control, and machine learning. This has been a longer kind of study in my group for the past few years. And so this is kind of the culmination tutorial, trying to figure out what did we figure out from trying to read all of the literature. I've got to preface it all with this will be very short and biased, and so we're going to probably miscitate everybody's work. And I apologize, and just bug me afterwards, and we can add you to the citation list. It's a huge and growing field, and it has very long history. And what I want to do today is try to give you a quick tour through it from a very particular perspective, which is if you had come up as someone who knew control theory, maybe, how would you actually go and jump into this reinforcement learning space? Now, why is that the perspective I take, other than the fact that I'm from a controls background? Much of the success of reinforcement learning, and it has been tremendous success, has been in environments that are very controlled, like games. And we've defeated the hardest games that humans can play, notably Go. But as we then try to move from the situation of games to where we have to interact with the real world, many new problems arise. And notably, the problems that we really have to care about are that these physical objects are going to interact with people. And we already have these physical objects based on machine learning systems actually ending human lives. And that's scary. This is something that machine learning never had to grapple with in its history until now. And so that our technology is at the forefront of engineering, and our technology is being pushed into all these situations that have to interact with people. It means that we have to step up and take new responsibility over the outcomes of what we do. So, in particular, the kinds of problems I want to look at today are exactly those that interact with the physical world and perhaps have this kind of view that might come from a bit more classical of a background. So for me, what reinforcement learning is, and this is we can all debate the actual definition, but I think at its most broad, is trying to understand how do you use past data to enhance the future behavior of a dynamical system. And from that perspective, if you had been a controls engineer, you might say, wait, that's control theory, right? So what is that distinction? In some sense, that distinction mostly comes from which department you did your undergraduate in. If you were in a department which has an E in it, many of them, then reinforcement learning is a bit of a subset of control, and it's taught that way. On the other hand, from a computer science perspective, reinforcement learning is really the primal theory, and controls is this very ornate thing that's a very special case. Taking our kind of prejudices aside, for me, control theory has always been focused primarily on continuous spaces and actually primarily on continuous time. I'm not going to talk about continuous time today because computers do compute things discretely, but we will be talking about continuous spaces, whereas reinforcement learning starts with a very discrete view of the world. The other thing that's primal in controls are models. Models are things that we are supposed to derive from physics. And perhaps all we're going to have to do is estimate a parameter or two. We never actually have to go in and learn a model necessarily, loosely. In reinforcement learning, data is really the key. Right? Everything in reinforcement learning is how do you take data and just turn it directly into actions. And I guess the other main difference between controls and reinforcement learning, right, is that controls gets published in very stuffy IEEE journals, and reinforcement learning, of course, gets published in the front page of the New York Times sometimes. Right, so different in their PR departments as well. So today what we want to do is try to just unify these two camps. And we're going to do that in a funny way, which is what we're going to do is we're going to try to solve continuous problems using the techniques from reinforcement learning. And we're going to see what insights that gives us. And we're going to see what we can learn from both of these communities. And then I will pose an endless list of problems and questions that I just don't know how to answer. So we're going to get a baby step today. And the number of things I don't know is uncountably larger than the things I do. Okay, so as I mentioned at the beginning, the kinds of things I'm interested in is trying to understand what are the limits of learning systems that interact with a physical environment. And I'm going to kind of narrow that down a little bit today to just talk about how much do we have to understand systems in order to do control. And the foundations of this will be, I'm a theorist at heart. There will be experiments that will appear in the talk. But at its foundation, it's going to be trying to merge the camps of a view from learning theory, a view from control theory, and for me, really, the most important thing here will be optimization. And so the core optimization will kind of unite everything. Okay, so control theory. It's really just the study of dynamical systems that have inputs. You have a system, you can play with this input, which is here U. That maybe will spit out some output Y, but in particular, it has some state X, and the X will evolve according to some update law. Okay, so the next state is a function of the current state and the current input. And today, we're not going to bother with the output being anything but the state. So it's kind of the simplest setting. So X is the state. I will always have dimension D, and remind me if you'll see something else. And U is the input, and it will have dimension P. And when these come up, I'll try to remind us of what those dimensions are. So reinforcement learning is kind of starts from the same place, right? It's the study of discrete dynamical systems with inputs. And in this case, the object that we use to describe how the discrete system evolves is an MDP. A Markov decision process. So in the Markov decision process, the probability of the next state is simply a function of the current state and the input. And in some sense, this is what defines state. State is that what I need to predict the future. And the main difference between the Markov decision process setting and the control setting is that these are taking their values in discrete space rather than in a continuous space. So there are D discrete states, P discrete inputs, and everything can be described now in terms of tables rather than some kind of continuous functions. Okay, so I'm almost not going to talk about MDPs at all after that introduction. This is just to make the connection. If you don't know much about MDPs, there are a variety of tutorials out there that I will recommend on the webpage. But what's nice is that this is usually where reinforcement learning starts. We're going to start with this other model. We're going to start with this control. Oops, this one. We're going to start with this model and see where we can go. Okay, so let's do that. Okay, so now optimal control is just trying to solve an optimization problem to make a control system do something. I have this input U. I want to find the U that gives me some properties out of from the X's. So here I've broken the input up into two. There's U, that's the thing I can control, and there's E, which is some signal I can't control. E is some kind of either an error or exogenous input or whatever you would like to call it. It's something I can't control. And today I will always assume that that E is stochastic. Okay, it's always a random variable. You can make your life harder if you make it adversarial. Okay, so now we have a state transition function. That's a function of the state, the input, and the disturbance. The cost function is given incrementally over time by some cost CT. This is another difference between reinforcement learning and control. Optimization, especially optimal control, is always minimizing costs. And reinforcement learning always maximizes rewards, which is kind of a glass half empty, glass half full kind of perspective. Control theorists are very pessimistic people. That's just kind of the nature of the field. So we're going to minimize costs. ET is our noise. FT is our state transition function. And here, I'm letting it change from time to time. I'm just being as general as possible. For most simple settings, people typically assume that this is stationary, so it's the same F at every step. Okay, so now here's the really important thing. Tau is the trajectory. Tau is essentially everything I've seen from time 0 up till now. And the input to the system is just some function of that trajectory. Okay, so it's not a function of the future, it's just a function of all the data I've seen up to now. So the decision variable here is this function pi, which we call a policy. And a policy is simply something that picks out an action based on everything I've seen before. Okay, and so that's the decision variable. That's somewhat complicated. There are lots of different ways to parameterize and write those down, but that's the thing we're searching for, is this policy. So there it is again. Just hold that for 1 second. Cost, transition, policy. Okay, so let me do an example to motivate this, and it's very simple. And that's trying to go fly a quad rotor. We want to get the quad rotor from point A to point B. And so we have to model this. And fortunately for us, the models are handed to us. We don't necessarily have to learn them. And the simplest model would be Newton's laws. And Newton's laws would just say that position, z, is the old position plus the velocity, up to constants. We're just scaling everything so that's true. The velocity is going to be the velocity plus the acceleration. That's how that updates. Just saying that the derivative of velocity is acceleration, the derivative of position is velocity, and then F equals ma. Okay? And if I put those together, that actually gives me a state representation. And it's very nice. It's linear in this case. So the output of the new state is a linear function of the current state and the input. And now, what should we do for a cost? So for a cost, what we're going to do is, this would be 1 if I'm not on the blue dot, and then 0 if I am on the blue dot. And if I look at that, it seems, maybe you guys can solve this, but it seems like that might be hard to optimize because it's very discrete. So what people do in controls is typically come up with a surrogate cost. So instead of minimizing this discrete cost, I would minimize a surrogate cost, like the sum of the squares. And this is just saying this will be larger than 0 if I'm not on the dot, and it will be 0 if I'm on the dot, so it's capturing something. And this is very much like what we do in machine learning. We don't minimize a 0-1 classification error. We minimize some kind of surrogate. Which surrogate you use is a design question, and then the analysis goes into proving that that surrogate is the right thing to do. So it's the same in controls, and here we could even add maybe a quadratic function of the input as well. Right? And so we can design a cost function and then say, well, how well does this do to solve the problem I initially cared about? Okay. What's nice about what I just posed is this is quadratic. It has linear constraints. You can write down the KKT conditions and solve it with least squares. Or if maybe you're a little lazy, you could call CVX. Or perhaps you could run back propagation on this as well. A variety of different options. That might be slow. What's also interesting is I have this parameter r here. R is essentially some trade-off between how much power I use and how much and how quickly I go to 0. And here I'm just going to graph two values of r. Here's the solution paths for time and position. And again, we're just trying to get the position to 0. and the solution paths for time and the control action u. And what you see is that when r equals 10, it's clearly trying to minimize the amount of control action that we apply. And it takes longer to get 0. Whereas for a larger value, a smaller value of r, when r equals 1, now we go to 0 much faster, but we exert a lot more force. And what this is also showing is that there isn't necessarily one cost function that we want to optimize in controls, which makes it a lot more challenging than in classification. In classification and regression, usually there's one cost function. There's some error that we'd like to minimize. In controls, and when you're actually designing systems, there are lots of constraints that you have to satisfy at the same time. So you may have a limited battery, so you can't use too much force, and you might have a fixed time that you really have to get to the origin, and you have to kind of account for all of these in the optimization design. So the cost function itself is not given. It's something that is part of the design process, and it's something that is typically iteratively refined. Okay, so there's our quick example. This turns out to be a specific case of a much more general problem, which is called the linear quadratic regulator. So linear quadratic regulator is optimal control. My cost function is quadratic. My dynamical system is linear. So there's linear dynamics. There's a quadratic cost, and hence it's linear quadratic. And we call this LQR for short. And I'm going to refer to this throughout the talk as a very simple baseline that allows us to compare and contrast different approaches to the general optimal control problem. Okay, so optimal control, back to the more general case. How would you solve it? I told you how to solve LQR. Turns out that the way you would solve LQR is sort of how you would solve the general problem, even when f is nonlinear. If everything is known, I told you the model, I told you the cost, you can either do batch optimization, which will be probably non-convex, but this kind of looks like a computation graph. So though I was joking about it, you can immediately write down a PyTorch graph and solve it this way. So just do back propagation. You could also use a non-convex interior point solver, and many of my colleagues who do this sort of thing will actually use software like IPOpt or SNOpt, and they will give good solutions. Or there's this general principle of dynamic programming, which you can't always do, but when you can do is quite efficient. It tends to be linear time in the time horizon. Okay, so if I knew f, then I could either run dynamic programming or batch optimization. If I don't know f, then the question is, what do I do? Okay, so if I don't know f, oh man, fire code. If I don't know f, the question is, what's the right thing to do? And actually, this is really where we start. That was your quick introduction to dynamical systems and control, and now we're back into machine learning. I don't know f. I do know, well, I don't care if you know C or not for this talk, but like I said, the cost is usually something you design, so let's just assume we know it. But then the question is, what do I actually do if I don't know the dynamics? And so we're going to try to reinvent reinforcement learning to solve that problem. Okay, so let's do that. So let me motivate that. When do we not know the dynamics? As soon as we move to something slightly more complicated, there are a variety of systems where it's actually sometimes hard to get a full dynamical model. So let's motivate it with what the reinforcement learning people motivate their research with, which, data center cooling. I love this problem. I love this problem mostly, again, because it shows that control people, my control theory friends, they have the worst PR departments in the world. Because data center cooling is, the control theorists would call it air conditioning. And it's really hard to get kind of like a flashy write-up in the New York Times if you just, figure out how to solve an air conditioning problem. So how would you learn how to cool a data center or a room like this? So there are a variety of different techniques. One, I could build a finite element model of the data center and have a full ordinary differential equation of everything. That seems like overkill. for a variety of reasons, especially because people reconfigure their data centers on a daily basis. I could do what the air conditioning people always tell me to do, and in which case you have you build a kind of much coarser model with heat sources and sinks. And this is actually what would be typically done in air conditioning. And this would just be an ordinary differential equation model with temperatures and changes in heat. Or I could be really cavalier and say, let's not do any modeling whatsoever and just try to find a function that maps center state to action. Okay, so those are the three possibilities. We could either identify everything, and there are actually applications for that. In particular, this is a turbine, and for really high performance aircraft, you really do want to identify everything because you're pushing up against the limits of what's possible. You can identify something very coarse, which would be kind of what I was arguing is probably what people actually do in practice for air conditioning. And this kind of underlies what we call model predictive control. They have people leave. Is there no way they can stay? Okay. 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 Sorry. That's unfortunate. Well, I don't know what I do at this point. Okay. All right. So that's all. I apologize to everybody who has to leave. I'm sorry. That's unfortunate. Right. So that got to my one funny joke, but unfortunately interrupted by the bouncer. That will happen. Well, friends, it's on Facebook Live. Where's the link? Thank you. Okay. Thank you, Francis. So let's thank the General Chair, Francis Bach, who has arranged for this to be on Facebook Live soon. Are you going to tweet it? It will be tweeted. It will be tweeted. Okay. Good. Fine. Back to action. We don't need no sticking models. That's us, right? That's everybody who's here. That's the machine learning point of view. And right, that's kind of, I think that's at the core of what people do in reinforcement learning. But I want to make an aside with this one, because while it seems crazy that this is what happens in reinforcement learning, it's also what we do in PID control. And I don't know who's learned PID control. Some people? Anybody? Okay, good. What's PID? That's good, right? So what's PID control? PID control is kind of, it's this funny thing where 95%, go ahead, Yisong. We're good. You want? I like this. I like this. The actual chair. All right, so we've got it worked out. So what is PID control? PID control is, is probably 95% of the control systems in industrial production are PID controllers. Now, that's a rough estimate, but people have actually done surveys of thousands, tens of thousands of systems, and found that what people implement in practice is PID control. And PID control is incredibly simple. Typically, you have one signal that you would like to make to zero. Like you want to stay in a lane in a self-driving car and not crash into the divider on the 101. So what do you do to stay in the lane? I know it's a dark joke, but it's, anyway, what do you do to stay in the lane? You first assume that your vision system is perfect. Okay, once the vision system is perfect, then what do we do? So then you have this error signal, which is staying in the center of the lane. That's some time series. My control signal is just the deviation from the center is going to be some error. And what I'm going to do is come up with an input that's a combination of the error, the derivative of the error, and the integral of the error. So it's proportional, integral, derivative. 3 parameters. And you typically don't need a model to actually set this up. There are heuristics that actually do very well in practice that automatically tune these parameters without a model. And moreover, most people don't even use the derivative term because it's very hard to tune and it's very sensitive. So 2 parameters suffice for about 95% of control applications. And now the question is, as we move, well, one question is, do we have to move beyond that? maybe. But then, so for this remaining 5% of the really challenging things where we'd like to add some learning, some control, something more sophisticated, how much of a jump do we have to make? Do we have to go from 2 parameters to 20 million parameters? Or is there something in between? And that's the question. So that's what we'd like to know. Okay, so with that motivated, here's our learning to control problem. Just wanted to put that back up to remind us where we are. And so how might we actually, before we even talk about how to attack that, let's set this up as a bit more of a math problem. Okay, so let's actually define the parameters. And the parameters here are going to be the following. We can generate n trajectories of length t. Okay, n trajectories of length t. And so the time horizon is t here. We can generate n is arbitrarily many. And then the challenge is we want to build a policy or a controller which has the smallest error given that sampling budget. Okay. And so n and t here are going to be equally, I'm just going to weight them equally. You don't have to actually do that. It may be more expensive to run lots of experiments so that t is getting a long time horizon is easier than multiple experiments. Or it may be that multiple experiments are easier than a long time horizon. I'm just lumping them in as a product today. I'm trying to make it as simple as possible. And the question is, what's the right thing to do? That's my oracle. What's the right scheme to do? You can already see it's more complicated than what we typically do in optimization at ICML, where we have just a function oracle or a derivative oracle. Here we have something a little bit more complicated. We could treat it just as giving us function values, because we can accumulate the rewards. But we have a lot more structure under the hood. And we should try to take advantage of that extra structure. So our big question is, how many samples do we need to actually solve that problem? Let's see what we can do. Okay, so to solve that problem, I'm going to first invoke my favorite design principle, which is the linearization principle, which basically says that if you have an algorithm and you think it solves deep learning, I want you to show me what it does on linear regression first. Or, if I had something that solves SAT, which is, NP complete, I want to see what happens on 2 SAT instances just as a sanity check. And this has basically been the last 4 years of my research and many of my colleagues' research. So this has actually been I feel like this gives a lot of interesting insights, starting with linear models, seeing what the complicated method does on the simple case. And a lot of times you can actually back out good insights about what's happening in the more complicated nonlinear space by looking at the linear case first. And a lot of times what happens in the linear case does inform the nonlinear case. It's not, it's not necessary that something that works on nonlinear models, something that works on linear models works well on nonlinear models, but you'd like it if it was working on nonlinear models to not be too bad on linear models. This is my axiom here. So I already introduced this one. For us, the simple problem, the linear case, I'm going to call LQR. What's cool about LQR is it's been studied forever. It has a closed-form solution. People understand the stability. People understand robustness properties. It's really just a very well-analyzed problem when we know A and B. And when we don't know A and B, well, now we can actually start to think, how does this compare? We can compare ourselves at least to what would happen if we did. The hard part with optimal control, when A and B, when this function is nonlinear and more general, is that even solving the control problem with perfect information might be hard. So here we're kind of going to something where if I have perfect information, I can solve it. It's well studied. I can do a lot of different kinds of analyses. And when I move to this kind of case where we have imperfect information, hopefully we can bound the gap. Okay, so we're going to use LQR as a kind of our foundation, but we're going to present methods that work on more generally. And so as far as I can tell, there are 3 general things that might work, and I'm going to lump names that come from the MDP land onto these 3 general things, but there are changes that have to be made when you move from MDPs to these continuous models. Okay, so the first thing would be fit a model to the data. And I'm going to call that model-based RL, even though model-based RL contains other things. For me today, model-based RL just means do some experiments, fit a model, use it somehow in the loop. Then there's model-free. Model-free RL has basically two sub-branches, and at least all the deep RL talks I've seen break it down into these two categories. Category one is estimate the cost function itself, the cost function of the entire optimization from data. So try to forget that there are constraints. Since there are quality constraints, these all actually is just one big cost function. Perhaps I could use regression to tell me what that cost function is and estimate it from data. And you'll see why dynamic programming becomes critical for doing that. And then the other one, which is the most cavalier, is direct policy search, which just says, let me just directly try to optimize for the policy without trying to fit anything else. Okay, so those are our three categories, and let's see where we can get here. So model-based. I like model-based because this is the only one that fits on the slide. This one fits on a slide. So yeah, anyway, it satisfies my simplicity criteria. Okay, so the first thing we do is we collect simulation data. And based on simulation data, well, we should have that the next x is some function of the current x, the current input, and the noise. Okay, and there will be some noise new that's different than E, right? So this is kind of our assumption, roughly. I put squiggles here to I'm being incredibly imprecise. Anytime there are squiggles, we're just going to take this as close to true. If it was actually true, what would you do? If I wanted to find the best phi that satisfied the equation, I would solve a least squares problem. And maybe you could construct a more complicated loss, maybe you could construct a more interesting loss, but that's probably what I would do at S-core, which is fit the dynamics using supervised learning, which we already understand. Actually, I was just at Colt, and the nice thing about going to Colt is you realize we don't even understand supervised learning, so let me not even say that. But we understand it pretty well. We know a lot about supervised learning. So once you have a supervised learning model, what you could do is now solve an approximate problem. Instead of solving the problem that we wanted to solve, we can solve this approximation. And the approximation plugs in some capacity, this model that you fit, and maybe models the noise that would be accrued. And so we have some approximation. Now the goal is just how far off is this approximation from what we started with. Okay. For people who've done controls, this is kind of the bread and butter of what the community has done. The first stage, these first two lines, are called system identification for controls. We call it supervised learning. And then when you take the system that's identified, you can design a control problem around the identified system. Okay, so that's kind of like probably was what most controls engineers would have suggested that you do. Okay, but let's be adventurous. We know that we've solved Go by other means. What else might we do? Okay, what else might we do? Approximate dynamic programming is a possibility. All right, so how does approximate dynamic programming work? This is really the core of classical reinforcement learning, is methods from approximate dynamic programming. Things that you have heard, whether they be Q-learning or TD or what else, PI or VI, policy iteration, value iteration. Help me out, Gergely, what did I forget? Which one? Q what? DQN? DQN, yeah, that's a good one. DQN, thank you. All fall into this box, right? DQN, that's a good one. So that's really, it's not just classical RL, lots of contemporary methods use this too. I'm going to just make a quick disclaimer, because I've presented this a couple times now. If you haven't seen this before, I don't think you're going to understand it at the end of my tutorial. And in some sense, this is why RL has been tricky for a long time. It requires an investment of time to understand the primitives, and it's worth spending the time, but in the few slides I prepared, it might not make sense. But it will be a taste of what happens. And so here's my approach. What I'm going to do is talk about dynamic programming, and then say, what does it mean to approximate the dynamic program? So let's rewrite our optimal control problem. Again, assume everything is known now. Now where everything is known. Eventually, so the machine learning will come in a second. If we knew everything, we could define this value here to be called the Q function. I'm calling it Q1 because it's from 1 to the final. And it basically says that if you start at state X and your initial action is U, what's the minimal achievable optimization value from those two initial conditions? And this is called a Q function or a value action function. Okay, so how do I compute the Q function? Well, if I started at the end, the Q function is easy. It's just whatever that final cost is. That's clearly what I'm going to accrue. And then you could get a recursive formula, which just follows from working from the back to the front. And it has this form, so that you add in the new cost, you have an update for the next state, and you have the Q function from one time in the future. So oftentimes this is called cost to go. Okay, and so this is at time k what the cost to go is from action u and state x. Okay, and you could derive this again just by dynamic programming. Work from the back, work your way forward. What's cool about these things, though, right? If I knew this Q function and I want to solve this problem, what do? Well, I know that this is the value taken for any x and any u. This will be the value I get running the problem. So what I have to do is just minimize the Q function with respect to u, and that will be the best action. And that turns out to be the optimal policy, and this is why people like these methods. You get this compact thing, which is to minimize some Q function subject to the state being xk. Now, let's put my optimization hat on for a second. In discrete land, where I have tables, that's usually where we motivate Q learning. In that case, the value action pairs are just a table, and then you fill in every value of the table, the value. And if I want to minimize it, I just look at the minimum value of a column. If I'm an optimizer, I note that this optimization problem is in no way necessarily easier than the one I started with. So even if I do the bookkeeping, it's not clear at all that I can actually solve the problem that I want to do in any way more effectively than solving this original problem. So you have to kind of build that in, that I have to be able to minimize this Q function well in order to have that. But that's an aside. In the continuous case, that's an extra complication. But in LQR, magic happens. Again, people love LQR because magic happens at every corner you look. So here's the cool magic here. Let's imagine I decided that the final cost is quadratic. I'm just going to assert, this is my optimization problem. Everything's quadratic. The final cost is quadratic. Then when I do this calculation out, which is minimizing with respect to the next action, the step into the future of Q, well, Q was quadratic. F was linear. So this is a quadratic. Quadratics are closed under minimization, and so I get a quadratic back. So I get some new matrix, pt plus 1, and this is my new step into the future, and then some reducible cost because of the error. So in order for this to work, the error has to be zero mean and uncorrelated with itself. So it just has to be white noise in some sense. So from time to time, independent. Actually, just uncorrelated to have this formula work. Okay, so that's my formula, and what I can actually write down, although it's absolutely horrendous, the formula for P. Now, where does this come from? It comes from minimizing a quadratic. If you've ever minimized a quadratic before, this is a sure complement, right, of some bigger matrix. So I just didn't show you the bigger matrix, which we did this sure complement on. And the optimal action comes out from minimizing this function, and you could pretty much read it off that this is the optimal action. So very cool. So this makes everything very simple. I mean, I could compute all this stuff offline. No, I mean, come on, you could compute it offline. To get these formula, you'd have to derive them. The derivations are not complicated. If I really wanted to torture my undergraduates, I can assign it to my undergraduates, but then they don't like they get mad when you do these kind of things. But it really is, there is nothing sophisticated here. It is just linear algebra and dynamic programming that gets us these formula. And what's particularly interesting is that if you take a limit as time goes to infinity and get an incredibly long time horizon, then you get a really interesting property out. So let's go back to this one real quick. One thing that's cool is that the optimal policy is a linear function of the state. So the best thing to do is multiply the current state by a matrix for the LQR. So it's a very simple policy, turns out to be optimal. On the infinite time horizon, the optimal policy is to multiply by a fixed matrix. There's some matrix, one fixed one you compute, and at every time step, all you do is multiply by that matrix. So that makes for a pretty simple controller. And the way you solve for it is you get basically you just take a limit of the equations on the previous slide. You get this matrix, which is kx, and the way that you get p is by solving this equation, which is nasty, but is doable. There is a SciPy routine that will solve this for you, so life is good. I don't know if it's in TensorFlow, but Google friends, the DR. This thing is called the discrete algebraic Riccati equation. We should add that. And the dynamic programming here has a simple form because quadratics are a miracle. And this is also probably why we study it so much. Quadratics have all of the properties you want to make this simple. What's also cool is the solution is independent of the noise variance. Your performance degrades the more noise you have, but your action doesn't change. So that's interesting. And finally, for finite time horizons, you could have just solved this with batch solvers. Okay. And the last thing I'll point out, and we always overlook this in reinforcement learning, but I want to point this out. The optimal policy here on a fixed time horizon is not time invariant. So if you have a fixed time horizon, the optimal policy is not time invariant. You can search for the best time invariant policy, and people do this a lot, but that is not the optimal policy. So it's always good to keep that in mind. The shorter your time horizon, the less optimal they are. So there's a lot of things you have to worry about as you kind of get to these terminal conditions. Okay, that's LQR to teach everybody dynamic programming. Again, there's no machine learning yet. This is just crazy controls. Where's machine learning? Here we go. Machine learning is this stage. So this is the crazy idea, and I love it. And it uses one of my favorite things that's ever been invented. So we're in math. So it's really cool. We have this recursive formula for the finite time horizon. On the infinite time horizon, well, to make our lives easier, we can introduce something called a discount factor, which is some number that's less than 1 that damps things off to infinity. And this just makes my life, like, limits always exist once you introduce the discount factor. It's saying way out in the future, the cost is exponentially small. And so if I have a cost that's being discounted and I have a static stationary update, now I have these two Bellman equations, and you get a fixed point operation, which is that the Q function is equal to some nonlinear function of the Q function. Okay, so how do I solve something where I have a linear equality constraint? Well, I could say, roughly, that if I were to actually take that step out into the future, this equation should be true, that the Q function at the current state and the current action should be the cost plus the min action over the future state. And if I've observed xk, and I've observed uk, and I've observed xk, I could just run gradient descent. And this is Q-learning. Q-learning is just saying, I have this fixed point equation. I'm going to solve that fixed point equation using stochastic approximation. In this case, because it's not the gradient of anything, we have a fancier name. But the analysis is exactly what you would have done in the original Robinson-Monroe paper, although it gets quite tricky for general Q functions. Okay, but it's cool. I got this simple update, and I can just run this. And this is, hopefully, if all of my ducks in a row, will allow me to effectively learn a Q function just from data. Now, again, for the tabular case, where all I have are discrete states and discrete actions, then this is a very well-defined update. When I have functions and function approximation, things get messy. I'm not going to go through that today because we'll all really be in pain. But again, it's not too much effort to adapt this to that case as well. Okay. All right, one last approach. So that was approximate dynamic programming. It's heavy. You do dynamic programming. You realize that in the infinite time horizon, I have this nice fixed point equation, and then I attack that fixed point equation using techniques from stochastic optimization, or in particular, stochastic approximation. And that is, in the theory land, pretty much what people study when it comes to RL. Now, that was until 1999, where, because this caused pain and suffering in the 90s, because all the analyses are hard, trying to get good guarantees was hard, and sometimes when you introduce function approximations, when you move to the continuous space, you can't even prove these things converge to stationary points. You can't prove they converge to anything. So in 1999, some folks published a paper at NIPS that proposed something, actually, no, sorry, different. In 1992, somebody published something at NIPS that proposed an algorithm, which I'm going to go through today. And then in 1999, it was analyzed that under function approximation, this works quite well. And that's the idea of just being cavalier and going directly at the policy. Okay, so I'm calling this broadly direct policy search. And since this is broadly direct policy search, I'm going to actually introduce it without any of this stochastic optimization business and just introduce it as optimization. Because you can kind of get everything you want to know about how to do policy search from the idea of sampling to search. So in this case, there's no dynamics. Let's take everything out of it. Let's just try to optimize. We want to minimize a function phi of a variable z, and I just want to solve that minimization problem. And now let me do some sleight of hand to come up with a crazy way to solve it. So the first thing I could do is instead of minimizing over variables, I can minimize over probability distributions. There was a long time at NIPS where this is all we ever did. If you're a variational person, you love this stuff, right? So it turns out these are completely equal because I could always just put a delta function at the z I want. So these are completely equivalent things, but optimizing over probability distributions is hard. So what you typically do is make an approximation and optimize over parametric probability distributions. Okay? So what I want to do is minimize the expected value of this function subject to a parametric form of the probability distribution, and I'm just going to optimize the parameters to get the smallest cost. And then I can sample from that distribution and get z's that should have low cost. At least that's the idea. Okay? That's roughly the idea. And what's cool, and I think why people love this, is that Williams showed that you can get a really cheap stochastic gradient formula for this second problem. And it goes like this. Let's call that function j of theta, because z is no longer in the picture. That now is just j of theta, because we integrated z away. The gradient of j with respect to theta is the expected value under this distribution of the function value times the gradient of the log of the probability. It's actually not that complicated a formula, and we can derive it very quickly. But the key thing is, if I were to sample z from this distribution parameterized by theta, this thing inside the expected value I could just compute. If you know the probability distribution, I could hopefully compute the gradient of the log of the probability distribution, and then you can multiply by the function value. And so the algorithm, okay, it's going to do this backwards. Let me derive this formula first and then show us how to run stochastic gradient. The derivation is super cute, which is another reason why I think people love this. And it's kind of the same trick that you use when you prove the Cramer-Rao bound, which is that if I take the gradient of this function, that's just the gradient is not going to do anything to z. It's only going to do something to the probability distribution. And then I could just multiply and divide by the probability distribution. Anybody who's seen the proof of the Cramer-Rao bound has seen that trick. And that now is the gradient of the logarithm. That's it. That's it. So this is now the integral of this function with respect to the probability distribution, also known as the expected value of that function. And so this gives us an algorithm. This gives us an algorithm which is to sample z, plug in this formula, and treat that as a stochastic gradient. So that's it. Sample z, compute this gradient approximation. This is an unbiased estimate of the gradient of j, and hence I can use stochastic gradient to solve this problem. And this is called the reinforce algorithm, usually with all caps, but I don't like the all caps. I think it was an acronym. Anyway, just pick the name. Okay, so this sounds amazing. Let's use this to solve something. Here we go. So let's say I have an arbitrary function on the hypercube, -1, 1. So it takes values in bits, and it's an arbitrary function. So I need a distribution to sample from the hypercube. How about just a Bernoulli distribution on every coordinate independent with different parameters? That gives me a parametric distribution like this. And so here's my algorithm for minimizing functions over the hypercube. I will evaluate the function and move that way. So I'm using this example to point out something that you always have to consider, even though it's not obvious, is that I don't think this solves any problem. I don't know what problem that solves. My guess is nothing. Or nothing interesting. I'd be curious to see which class of functions this actually would minimize effectively. And because it's not using any information whatsoever about phi. And hence, it's kind of lumped simple functions, like linear ones, in with arbitrarily complicated functions, like random ones. They're treated the same. And so maybe the dynamics can make sense of that, but that's something you have to prove. And it's not at all clear that this is actually going to be something sensible to do. Okay? I just want you to keep that in mind as we now apply it to control. So this one seems absurd, but then we just go and do it to control, and it feels like, is it actually working? Why is this absurd? Well, look, we have to take an expected value with respect to this small class of probability distributions. It's not all probability distributions. It's a restricted class. And that might actually hamper what we can do. So by restricting to that class, we actually have to understand what that restriction is costing us. Okay, but let's plow ahead. Let's plow ahead. And I'm going to plow ahead and introduce, this is not what people typically use in RL, but it is what a lot of people have been using in robotics, and it's called parameter perturbation. So this is if I have this cost function, this would be, so what are we going to do? We're going to add we have a policy. The policy is going to be a parametric function, has some parameter vector theta. What we're going to do is just add a little bit of noise to that parameter vector and then estimate the value. Estimate how good that perturbation is. Okay, so that's our random sampling. We would integrate over this. And it turns out that what this algorithm does is the following. It's equivalent to the following approach. If I were to write the cumulative cost of the sum and let my perturbation be Gaussian, then what I would do is I would add a little bit of Gaussian to theta one way, add a little bit of Gaussian to the theta in the other way, and then it turns out that the log of the probability distribution is going to give me a omega I out here. So what this ends up being is a finite difference approximation to the gradient in the span of these random omegas. So in this case, this algorithm gave me something maybe that looks somewhat sensible, right? I mean, what I've done is I have a function. I can't compute the derivatives of the function, but I can approximate them using finite differences. And now we're approximating the finite differences in some random subspace. This particular instantiation is never called reinforce. So it was initially called random search by Rastergan in the 60s. It was discovered in evolutionary algorithms sometime in the 70s, and it's usually a mu-lambda evolution strategy. And I can't remember what mu and lambda correspond to here parameter-wise, but probably sigma and m. It was also invented by our friends at Stochastic Approximation, by Spall. And it was also invented in the learning theory community, and it's called bandit convex optimization. And it's usually my feeling that if you have an algorithm that is developed independently by 4 different communities, they're probably onto something, right? That's just signal. Okay, so we're gonna come back to this one. I call it random search. I know a lot of people hate that, but I'm just gonna stick with what the Russians called it, because they get mad too. Don't cross the Russians. Bad things happen. Okay, so policy gradient is different. Reinforce is usually used for this algorithm called policy gradient. And policy gradient, what it does is it actually just replaces a deterministic policy with a randomized policy. But this is no different than what we were doing before. It's just saying that the value u, instead of being a deterministic function, is now a randomized function. And in continuous spaces, it's worth noting, I probably should have written this on the slide, but in continuous spaces, what typically you do is you take a deterministic policy and add noise to it. Okay, so that's not perturbing the parameters of the policy, it's perturbing the outputs of the policy. And that's the main difference between policy gradient and random search. And it's actually hard to write down exactly what this formula looks like, but we can do it for LQR. And I think it's instructive that you could say, let's say I wanted to solve a finite time horizon LQR. I could assume that it has a stationary policy, and then I can perturb the stationary policy by noise. So at every time step, I add noise to the action. Then I can compute the cost, and this is the update. So the update uses the state, it uses those noise directions, and it just evaluates the cost. But note that it has no It has no gradient information about the cost. It has no gradient information about the matrices. In fact, it's like completely independent of the dynamics. So this is one of these things I always find frustrating. It is certainly a gradient method. The reinforce algorithm is a stochastic gradient method. But for the functions we care about, which is the minimizing the LQR problem, we only get function estimates. So it's a gradient algorithm on a function that we might not necessarily care about. Again, it's worth emphasizing that. This is essentially a derivative-free algorithm because we never compute derivatives of any of these quantities that we care about. And in particular, then it suffers from a lot of the complexity results that go along with zeroth order optimization. So again, there are two different categories here that we're covering. There's policy gradient, there's random search. Reinforce applied to either of these problems does not depend on the dynamics, and I think that's really cool, and that's why people love them. Not only does it not depend on the dynamics, it doesn't depend on you knowing how to compute the cost function as long as there's some oracle handing you the cost function. So if you have some kind of simulator or video game, as long as a score is returned, you can apply the algorithm. And I think this is also why they're exciting. I could just go. This is actually kind of what's, I feel like really what differentiates computer science from the other engineering schools on campus is like at the end of your first lecture, you're doing stuff. So why not just do this too, right? They're much more fearless. Now the question is, does it work? How does it work? Can we analyze it? How does it compare to other techniques? That's the next step. And I would like to emphasize that they're both derivative-free algorithms, and I'm going to keep saying that. Okay. All right, so to sum this up, reinforce is not a magic algorithm. You have to be careful both about the approximation error, and another thing I didn't mention, the variance. When I run stochastic gradient descent, you care about the variance of that gradient. And if the variance is really large, you will never converge. So those are two things you have to take into account. You want a small variance estimator of the gradient. You want the approximation error to the true function to be good. And you have to be able to sample. It's a lot of burden on you, which I might call modeling, honestly. So even though it's model-free, there's a lot of modeling that kind of goes in under the hood. And again, I'm going to say this again, it's necessarily derivative-free. Okay, but it's easy. And that's what makes it exciting, and that's what lets us plow ahead. Great, that's great. So actually, this is a perfect time. Let's take a 10-minute break. We'll reconvene, I guess, at... I could be really precise because I have the clock here, but that's probably dumb. You guys don't have the clock. So let's reconvene at 5 to 5. Francis.
So the talk will be live streamed in A7. So when you come back from the break, if it's full, go in A7, exact same band, but on video.
Awesome. A7. Thank you again, Francis. All right. And so, so let's come back at, actually, I would say 10 till. Let's do 10 till. That would be good. 450. 450. Good. All right. Thank you. let's get restarted. Hi.
Announce that people must be in a seat.
Yes. No, I got it. We're good.
You know that we're live streaming over at A7.
That's right.
Okay, so
Gison's got it.
just FYI, there is an overflow room with a live stream in A7 just down the hall.
That's right. And unfortunately, if you can't find a seat, you have to go to the overflow room, or else that guy's going to come back. I don't want you to. He's even mean. Cool. All right, let's do this. Where were we? We left off at everybody's favorite part. Well, no, actually, I don't think anybody has this favorite part. We left off is when we move into learning theory. Okay, so I want to do just a little bit of learning theory, not too much today. But this is actually something that we grapple with throughout RL, and in some sense, half of the papers in reinforcement learning that I see discuss a notion of what's called sample complexity. So sample complexity means a very particular thing in learning theory. It means a slightly more nebulous thing in reinforcement learning, and I kind of just wanted to touch on that. Here is, again, this only other slide that has the MDP formulation, even though we've been talking about the tabular case off and on. The idea here is that, again, I have a discrete vector x, or just an x that takes only discrete values. It's not a vector. X is the values 1 to d. U is values 1 to p. And I have an MDP. And the question is, what's the relative complexity of these methods? Something you should take away from that first half of the talk is we saw that in model-based methods, at least from my narrow view of model-based, what we would do is we would take data and then we would solve essentially a system of equations, right? We have measurements, and each of that gives us equations, and then we have unknowns, which could be the model, could be the Q function, or could be the policy, right? And the question is, we can now do parameter counting to get some rough rule of thumb as to which one may or may not be more efficient. Okay? So this is one way to maybe try to decide which of these methods are best. So there are 3 algorithm classes. So in the MDP case, for model-based, we get the value of the state, and we're just going to use the value of the state to predict what the probability of the transition is. For approximate dynamic programming, we get the value. And also for policy search, we get a value. And each of these gives us one equation for every time step. Now, how many parameters do we need to identify in the most general case? Well, the number of numbers required to give me the state transitions is just d squared p, right? And this is just counting because it has 3 arguments. That's pretty. The discrete world is nice. Very easy to count things. Approximate dynamic programming, we need a Q function. The Q function has a value, takes a state and an action. So it has d times p parameters. And policy search, what does that do? Well, if for every state, it gives you an action. And so that would also have d times p parameters. This is not parametric. This is actually just trying to write down what those mappings might look like. And so the optimal error, if I were to write it down and guess what would be optimal. So again, this is very naive, and this is just chicken scratch on a piece of paper. What would it tell me? Would say that roughly these are sample complexities. So sample complexities have parameters in the numerator and then number of samples in the denominator. And they suggest that probably ADP and policy search are more efficient than a very broad fitting a model approach to model-based RL. That's rough. I mean, again, it looks like that should be the case. It looks like that should be the case. So assuming we know nothing about the model transitions, it looks like that would probably be the hardest, and then ADP and policy search should be easier. But there is no algorithm that gets these complexities currently out there. And if you're into this kind of thing, there are all these papers written by bandits people who try to get these numbers as small as possible. Now, let's now go to the continuous world. In the continuous world, we can do the exact same thing, and the story completely changes. It's a very different kind of setting. In the continuous world, we get more samples per iteration when we have a model. Let's think about the least squares problem that we solve, right? We observe the state. There are d elements in the state, and I get a mapping from a model to the state. So there are d equations per time step, whereas approximate dynamic programming and policy search are still only using values. Moreover, Once we moved to the continuous case, we actually worked out what these things were. The Q function in approximate dynamic programming has d plus p over 2 parameters, or sorry, d plus p choose 2 parameters. So that's a quadratic. It's d plus p squared. The policy has d times p parameters, and the model-based has d squared plus dp for LQR, right? For LQR, it's d squared plus dp. You have a square matrix for the state, and you have a rectangular matrix for the control. And so if we put that together and we get our rough rule of thumb, it seems like the model-based approach might require about d plus p over t to the square root. That should be roughly our error if life was good and everything worked out with parameter counting. Whereas approximate dynamic programming might suffer a factor of dimension, and policy search might be somewhere, depending on the size of the parameter, either about the same or maybe a little worse, right? Because the product should be bigger than the sum. Okay? Rough rule of thumb. But it looks different, and the question is, in practice, is it actually end up looking different as well? Are these model-free methods making effective use of the information that's given to us? That's really the question we have to figure out. Okay. And of course, I do want to point out again to everybody here that there's a constant that, of course, is going to go out front, both in the MDP case and in the continuous case. And a lot of times, I mean, this is now for my theory friends in the room, a lot of times the interesting stuff is actually happening here, not here. So just worth keeping that in mind. Maybe there's actually some other complexity that comes out up front that's more important than parameters, and let's see if we can get at that as well. Okay. And I guess we could also talk, here's my, I can't come to a machine learning conference without a deep learning slide. This will be the only one. Deep reinforcement learning is, at least from my perspective today, was just the only thing that would change if you wanted to implement it would be that we would parameterize our Q function or our policy by a deep neural network, or maybe we make our model a deep neural network. Everything is going to be tricky to analyze in this case, but none of the algorithms would change. And again, this is why the linear principle is going to apply, so that hopefully we can get some insights, because nothing changes moving to deep networks other than the function approximator. So anyway, that's for next year. Maybe we'll analyze deep networks. We're going to just stick with very shallow reinforcement learning for the rest of today. And again, the reason why is because the algorithms don't change. Okay. So let's return to my friend LQR and start to look at sample complexity. Rather than trying to prove stuff, let's run some experiments. Because I like running experiments on these continuous problems. And in particular, let's run the silly double integrator experiment. In controls, we call this model a double integrator. And with LQR. And so what's this plot? So policy gradient is in blue. The error bars are over 10 trials, and it's kind of the min and the max over those 10 trials of what value is returned. After about 30,000 samples, we get something that is close to the optimal of the Riccati equation. So a lot of variance. To actually get this was a fun interaction on Twitter. I couldn't actually get it to work at all. And then a colleague tweeted, or actually I think it was on Reddit, somebody came up with a better implementation. My friend Pavel, who did a great job here, told me that what you have to do is, instead of running stochastic gradient descent, you have to run atom. So this actually requires not policy gradient, but atom. And I don't know why, but that's fine. So we added some extra stuff. We were able to get it to converge. People like atom. That's cool. And it does things. But so an interesting thing is that just fitting this model, not telling it anything about the structure, but just fitting it as a black box but linear model, and then just treating that as true and not doing anything, just treating it as true, is indistinguishable from this black line. Like 10 samples and you get the answer. And similarly, approximate dynamic programming, I implemented what was called least squares policy iteration, which is a nice paper by Lazarus and somebody whose name I'm forgetting. But it's a fairly straightforward. That also achieves this line. Okay, 10 samples. So there's this weird gap here where the policy gradient, as we said, and I did the vanilla algorithm that I showed in the first half, which was just you compute the cost, you multiply it by the noise times the state accumulated. And it is kind of what immediately follows out. But I've never been able to get it to do something nicer, even after tuning the parameters of Atom, of the sampling scheme, and what have you. And this is weird, right? Because policy gradient, I think, I'm told now is a straw man, but I'm told that direct policy methods are supposed to work, right? I mean, this is like apparently what OpenAI is going to use to defeat DOTA. And it seems like if it can't solve a double integrator, something weird is happening there. And everybody attributes this quote to Carl Sagan, that extraordinary claims require extraordinary evidence. But it was borrowed by Lance Armstrong when he was defending himself against accusations of doping. And so the important thing that even Carl Sagan and every good Bayesian would say is that's true only if your prior is correct, right? If you had the right, if you actually had the real prior, the claim might not seem quite so extraordinary. And so I guess the thing I want to say about these policy gradient methods is, like, if we look at what people who implement them say, there are red flags even in their own descriptions. And in particular, that reinforcement learning results are tricky to reproduce, performance is very noisy, algorithms have many moving parts which allow for subtle bugs, and many papers don't report all the required tricks. This is a quote from a blog by some of the folks at OpenAI on their DQN baseline. They also say that reinforcement learning algorithms are challenging to implement correctly. Good results typically only come after fixing many seemingly trivial bugs. I would like to ask them what a bug is in this regard. And honestly, I don't know who would actually put that in a car. And it's not just them. There's actually been a lot of papers about this. Joël Pineau gave a great keynote talk at ICLR, and I believe that video is still up, about some work that her group has been doing with her collaborators, trying to get at kind of how sensitive these algorithms are to a variety of settings. And in particular, there's this famous plot, and we're going to go into this plot later, which shows that if you change the random seed, algorithms can seem to have incredibly different performance. So 5 random seeds look one way, 5 other random seeds look some other way. And that leads to weird stuff. And I actually think this plot is the more scary one, because this is 3 different implementations of, I think, TRPO. Yeah, of TRPO by OpenAI in just 3 different Git repos. And in particular, 2 of them, the blue and the orange, it's the same repo, just a different release point. So 2 different release versions of the same repo have very different behaviors. And obviously, the first one is going to apply to the second one. Right? Because if you're sensitive to random seed and you just change the order of operations and how you access the randomness, you'll get different behavior. And so that's a bit worrying. So this leads to something that looks like reinforcement learning is incredibly challenging to implement. But now the question that I want to ask for the remainder of today is does it have to be this way? Or is there some other way forward for these kinds of problems where we're allowed to use machine learning? And in particular, can we use models when we start doing problems which involve continuous control, and does that work better? One thing I do want to point out before going to models, which I think is pretty interesting and worth kind of highlighting, is that if you just run the random search algorithm, which was pointed to me over the break, actually appears in Nemirovsky and Yudin. So it's everywhere in the Russian literature. So we're going to stick with random search. This algorithm, remember, perturbs the parameter rather than perturbing the actions. This actually achieves, in, I guess, 5,000 iterations, a pretty good policy. But it's still not, 5,000 versus 10 is still a huge gap. So even though it's a general purpose algorithm, again, the thing you always want to ask yourself is, even if you have a general purpose algorithm, how much are you paying for that general purpose? And if it involves a lot of variance and a lot of uncertainty, maybe it's not something you want to rely on. So obviously, we're at 5 o'clock, and I'm supposed to have another hour or so, and so yeah, of course, I have more content. So let me tell you some ideas, and that's our friend model-based RL, which I think has a particular, there are debates even in the MDP case about whether or not model-based RL is as good as these model-free methods under a variety of different settings. But I think for continuous control, it's actually, like we already saw, that the sample complexity conceivably is a little bit better. And moreover, maybe we can even try to analyze this for a simple case and see if that's actually true. So the one thing that's hard here, that's vague, supervised learning, easy. roughly, well understood. The hard part here is actually what control problem do we solve? Because just plugging in the truth or plugging in an estimate and treating it as true feels wrong, right? Even in machine learning, this is kind of why we have all of this stuff with, confidence sets and a variety of things. So how can we take into account the fact that we know this model is not perfect, and maybe we can even estimate how imperfect that model is? Can we actually take that into account in control? And the answer is yes. And the answer, this was something where if you went to a controls talk in the 90s, you would have seen this slide in everybody's talk. You probably still do if you will go to them today. But so here we have our system, which is evolving according to F. We're trying to design a controller. And what we do is we can estimate a model from data. Right? So F hat is our estimate. It's not the true F. So now we have a system that's F hat. Now we want to design a controller for the true F, but we only have F hat. Well, the key idea is, what if I could estimate the uncertainty in F and treat that as another building block in my dynamical system, so that I could account for not just F, but every possible instantiation of my uncertainty about F. So I could use high-dimensional statistics to say not only how good is this model, but how far is this model from, I can estimate how far my model is from the truth. So it's not just getting a point estimate, it's getting a confidence set. Once I have the confidence set, I could try to design a controller that works for every single function in the confidence set. And that is what we call robust control. Okay, so I'm calling this connected thing where we're coupling statistics with control, course ID control. And this is actually something that, for whatever reason, because the statistics wasn't there, I didn't really see in the controls literature. In the controls literature, they're much more into you take your you take the model that comes out and you treat it as certainty equivalent. But it's also possible, controls people love putting in these extra things about modeling errors, to just add those in. And the other thing that's interesting is we can estimate modeling errors. And we can estimate modeling errors of modeling errors if we wanted to, and we can have turtles all the way down. Okay, so let me describe how this might work, and it's actually kind of cute. And now it's going to get a little bit more mathematical than what we've had so far, but it's it's again, hopefully relatively simple for how this might work. So what I'm going to do is my analysis of the one step of LQR, just to show how this works. And I'm going to walk us through all the different steps and all the different machinery that we'd need. Okay. So we're going to say B is unknown. And I have this cost function, which is quadratic. And I have this equation, which is linear, right? And B is unknown. And so what can I do? Well, I can run experiments, collect some data. When I collect some data, I'm going to have that xi is equal to bui plus x0 plus ei. And maybe ui would be Gaussian. And then I could estimate b by just solving these squares. Now, what we all know is this will give me an estimate, right? This gives me an estimate for free. It's pretty cheap. What I think is less appreciated is, one, if we assume properties of the noise, we can actually estimate how small this error is with high probability. And it doesn't even have to be that restrictive of properties to get out these kind of epsilons. And moreover, if I could just run simulations, I could estimate how sensitive I am using something like a bootstrap. And if you use the bootstrap can give you a pretty good estimate of this epsilon without even having to work through the concentration inequalities. So whenever you build a model, you can test how accurate it is by bootstrapping. I imagine this is true for the deep case as well. I know I haven't thought about how you do bootstrap with deep models. But the deadlines are far away. So the ICML 2019, let's see that. Okay, so now here's kind of the idea for how we would actually turn this back into the optimization problem. And all we're going to do is note the very simple fact that if delta b is my error, if that's b minus b hat, and b hat is my estimate, then the x here is equal to the x here, because I'm just replacing b with b hat plus its error. This is very naive and silly, but what this lets me do is rewrite the problem into a robust optimization problem. So I can have just the estimate as the constraint. And this is what I had in the previous slide. This is the estimated model is my constraint, not the true one. But then what I'm going to do is write in the cost function the effect of that estimate. So the error now just gets pushed into the cost function. Once the error gets pushed into the cost function, I could take the worst one. Okay. So what I did was I took a problem that we started off with, which was just minimizing a quadratic. I took a square root because it made my life easier, as you'll see in a second, because I'm going to apply the triangle inequality. Spoiler alert. So I had to take a square root. But so once I did that, I could have now just nominal constraints, which are easy, and a robust cost. Okay, so this is robust optimization. And it's robust in the sense that what we're trying to do is we're trying to be able to solve the control problem for every possible instance of that uncertainty. Okay, so the trick, and this is actually the trick we use for LQR to actually analyze this, is that if you apply the triangle inequality and bound the maximum eigenvalue of Q, now I have a convex problem. The convex problem has introduced a regularized version of the original problem. And if people know robust optimization, this happens all the time. Uncertainty in data can be translated, robust uncertainty in data can be translated into a penalized problem on the model. And that's exactly what happened here. This is kind of, Laurent El-Gawi has really nice talks on this kind of thing. Okay, so, and we just did the triangle inequality there. Renee, do you have a question? I will repeat it. Okay, so Renee is asking the question, which is good. Why do we have to do this decoupling, a layering of estimation and then control? Which is a great question, and I don't think we do, but that's what we did. So in the work that I'm going to present, that's what we did. I don't necessarily think these steps have to be decoupled. I think you would just have to come up with a different formulation.
The reason is that potentially you might need many more samples to get B.
Correct. Correct. So what Renee is also saying is that this optimization problem doesn't know anything about Q. So we're estimating B without any knowledge of the cost we want to optimize. And that could be accruing a loss. But I'm going to punt on it because I want to get a finite result. The other thing that's nice for people who care about these things is a generalization bound on my model will turn into a generalization bound on my cost function. And that's also what I really like. So this is now one of these weird things. And again, this is kind of addressing why not do them jointly, is that we've developed a lot of techniques to figure out what the order of epsilon should be given properties of the measurement process. And what's cool about this approach is that if you have those, you have some model and you know some things about its deviations, those immediately give us ways to bound the error of the optimization. And that's kind of why I like this particular approach. And I can hear myself through the wall. That's weird. Okay, so hello everybody in A7. All right, now let's do this for linear systems. Let's do this for LQR. And I'm only going to do 2 slides. It's going to be very high level, and then we'll go back to experiments, which are kind of more interesting. But let's at least say, what is a theorem that we can prove? And I think that's kind of interesting, that we could prove theorems about all of these things for the LQR case. So what you could do is you could run an experiment for T steps, and then you could estimate A and B. And it turns out that actually is a weird optimization problem because all of the x's depend on A, and hence A depends on all the x's. Everything is very coupled. But with some analysis, you can show that this actually gives you a optimal in the parameters estimate of A and B. And you also have this funny matrix that enters in, which is a property of the system itself. So like I said, these constants actually do appear here. And what they say is that if a system is easier to excite, what this matrix lambda c is basically how much signal do you see from a random input. If the signal is easy to excite, this denominator is large, and the number of samples goes down that you would need. So signals that are easy to excite, systems that are easy to excite are easier to estimate. And if we just assume the worst case here, which would be the case when A equals 0, or near 0, you get an optimal dependence, at least on the parameters, which we had many slides ago I was hinting at. Then we could use this triangle inequality technique, albeit in a more complicated way, to actually analyze the limit version of LQR. It requires more bookkeeping because now it's an infinite problem. So doing one step was relatively simple, but even already a little complicated. This requires more bookkeeping, but is in a paper by Sarah Dean, Horyamania, Nick Motney, myself, and Stephen Tu. And there'll be references at the end. And it turns out that if you solve a relaxation of this problem, this robust optimization problem, you actually get that the error for the controller that I predict minus the true, the best thing you could ever do if you knew the model, divided by the best thing you could do if you knew the model. So this is a relative error. Scales as some constants, times d plus p over t. So this was exactly what we hoped by writing down what would be maybe the best case for model-based RL. We would be able to get that part we do get. And then we get properties that depend on the actual system we're estimating. How large is the gain? If the gain is large, you need to have more samples. How sensitive, this gamma CL is a very interesting thing. It says that if you were to design the optimal controller for the system and then blow on it, how much signal do you see? So the system is being stabilized by the optimal controller, and how sensitive is that to perturbation? The more sensitive that is, the more samples you need. And again, the easier the system is to excite in an open loop setting, meaning just there's no controller, I'm just doing experiments, the less samples you need. And so these things actually kind of come in, they kind of show an interesting trade-off. What's also interesting here is that this also tells us when the cost is finite, which is crazy. We are doing experiments on a finite time horizon and extrapolating to an infinite time horizon. We're extrapolating out to say, when is this actually finite? We're going to see in a second, not always. It's not always easy to do that. And this is actually giving us a bound of how many samples do we need to guarantee that we get finite cost. And I'm going to describe in a second why finite cost is very important for practical considerations. And yeah, let's go back to my favorite example. Let's examine why finite cost is important. Okay, so this is a very toy model of the Google data center. They have some cooling rack, some servers, and they put fans on them. And then the servers maybe shed heat to each other. And this is a really dumb model, but maybe this would be what that model would look like, where each server has some kind of activity that's heating it up. And this number is bigger than 1, so if I ran it open loop longer and longer, it's going to go to infinity. That's called unstable. The system is unstable. This is going to blow up if I run it without doing control. And if it blows up, the farm blows up, that's probably bad. Now I have a fan at every location, so I can cool it down individually. But if I want to get a really flashy result that I can get in the newspaper, what I really need to do is spend as little electricity as possible, because you need this PUE ratio that everybody makes a big deal about to be small. So I'm going to really penalize doing too much effort with my control. But that's weird. Now that introduces a tension. That's very easy to clarify what that tension is. This system is called unstable because it will go to infinity if you don't do something about it. But if I do least squares, maybe I estimate this guy to be 0.99. So if I did least squares and that's 0.99 and I want to save energy, I was like, maybe I won't control that one. But it was actually bigger than 1, and so it may blow up. And that's actually what happens in this simulation. We do see that behavior. I have 3 plots here. One is this kind of course ID control where I tell the true error between the estimated model and the real model, and that gets the blue curve. The green curve is where I estimate that using the bootstrap, and you see that there's some degradation. We did a very conservative bootstrap here, but it's not crazy bad. The orange curve is what happens when I just plug in the model. This is called certainty equivalence in control. It's the naive thing to do. Take your point estimate and pretend like it's true. If you take your point estimate and pretend like it's true, you see it starts to spike up here, and there's no data down here. So the cost seems to be, something weird seems to be happening earlier. If we turn to the second plot, what's happening is this plot is the percentage of the time that when I run a simulation, the model that's returned in closed loop is finite. How often is my cost finite? Finite cost means hopefully, at least roughly, finite cost means maybe your data center doesn't catch on fire. Infinite cost means definite fire. And so what we see is that if you give it the true cost, the true distance to the model, we actually get a nice curve, and after about 100 samples, are always returning nice, stable behavior. When you use the bootstrap, we're never getting a good model up until about here, but then we start to chase what the blue does. And what's cute is down here what's happening is our SDP solver can't find a feasible solution. That's also interesting, and this is actually something we always take for granted. If you can't find a feasible solution, it might mean that you have a bug. It might mean that there's something wrong with the model, meaning that perhaps there is no feasible solution. And this is why you don't want bugs in your control design software, because you have to be able to distinguish between which is which. Now, the nominal control is actually even out at 600 samples, so well beyond where we started. About 10% of the time is returning something unstable because of this model. So the least squares estimate, if you just plug it in, may yield an unstable controller, but the robust method yields a stable one. Okay, so on this plot, we return to our friends, which are model-free. Note that the x-axis is now 10 times larger. We needed more samples to make the comparison fair. This gray curve is our Russian random search, evolutionary strategies, bandwidth convex optimization, whatever you want to call it. So it's still about an order of magnitude off from the other guys, but it's doing something. The red curve is LSPI, and policy gradient is not here. Policy gradient is blue, which under the Klieg lights is a little hard to see, but it's this blue curve which we'll trace out here. And policy gradient has a hard time finding a feasible stabilizing solution, even 50% of the time after 5,000 samples. So maybe we could tune it to be better. I tried. The Jupyter notebooks are linked off my blog, so you're welcome to try to do better. But something has to be done here to make these model-free methods kind of outperform the model-based. So this is cool. We have this like end-to-end bound. This is new work. We have an end-to-end bound that goes from estimation error directly to control error for this LQR. And one question we were asking, because we were digging through the literature, why was this never done before? The biggest reason is just to get the least squares estimate actually required some heavy machinery. We needed to go to some probability papers that had appeared in our archive in the last year. So high-dimensional stats, basically the difference between 1995 and 2018 is this growth in high-dimensional statistics and our ability to understand it and our ability to analyze it. And that can now be plugged in to tools from controls, maybe from the 90s, and try to link these things together. That said, even the controls result requires some new results for controls. In particular, it's building on something called system-level synthesis that was developed by Nick Motney and his collaborators at Caltech. And that really was key to making this work. And I think the thing that was really cool about this is what we initially started to do was we were just looking at the solution, like the LQR solution comes out of this crazy equation I wrote called the algebraic Riccati equation. We tried to understand what happens to that as you perturb the parameters, and we got very frustrated. And we spent about a year of frustrating time on understanding the perturbations. But if you somehow restrict yourself to always be robust, the analysis also ends up being easier. So it's safer. And for some reason, it actually kind of makes sense. Because we're restricting in our class, the analysis is easier. The surprising part is it does look like this gets to something near optimal. And maybe that's the other reason why we're... What's really exciting is there's a lot of work in just like the last year on this problem. So there's all sorts of stuff I'm not going to talk about today, but like there are multiple results at this conference about LQR, which is really cool. In particular, you can prove that policy gradient if you start with a solution that doesn't blow up your data center, finds the optimal one. So as long as you could find one solution that doesn't blow up, you could find the optimal one with policy gradient. If you don't know it to begin with, you may run into some trouble. There's also all sorts of other work adapting LQR, and what I'm not going to talk about today is about adaptive LQR. There are like 10 papers that have just come out this year trying to tackle this problem. I'll talk about that again at the end. So it kind of really is just we're just really starting to understand this linear case. And I've had in quotations the entire time, simplest example. What's amazing is how hard and complicated LQR is. LQR is not simple. And it's like the simplest thing I knew how to write down, and analyzing it actually requires a lot of machinery, and in particular, a lot of new techniques. The one thing I'll say, if there are any theorists in the room, is that our bound required doing an analysis to avoid mixing time analyses. This is now just for the experts. So if you don't know this stuff, I just wanted to point this out, that most people who analyze time series use an analysis that depends on mixing. And the mixing analyses turn this minus 1/2 into a plus 1/2. Gives the exact opposite behavior of what we see. And there's about 50 pages on Cosmas Shalizi's blog that do that. So again, this is this case of working in the most generality versus the specific case. For these specific models, there's a lot of interesting work just in time series analysis to try to push forward. Okay, that was for the experts. Okay, so that's LQR. We're making progress. We're starting to just understand the basics of the sample complexity. But I don't think anybody in this room is that interested in LQR. It is a workhorse. LQR, honestly, is like, I said 95% of the things that we do are PID control. Of that remaining 5%, 95% of those are model predictive control. And almost all model predictive control, which I will talk about in a couple slides, is using LQR under the hood in one way or another. So it really is kind of like a workhorse algorithm. It's worth understanding, but if we want to go do some complex robotics, perhaps we need something more sophisticated. And so a question is, does the converse of the linearization principle apply for these problems? And all I'm going to do now is just look at some experimental evidence. I have no answer. I'm going to look at one case study, and that'll be the end, and then we got to see from there where we go from here. And so the case study is on this funny set of demos based in the Mujoko simulator. So OpenAI, actually starting with the work of the PhD work of John Schulman, probably even earlier than that, starting with work that Sergey Levine had done, people started to use Mujoko as a way of trying to do controls benchmarks for reinforcement learning algorithms. Mujoko is the simulator. You get guys that look like this. You can make all sorts of various robots. You can execute the dynamics forward. And then from executing those dynamics forward, you can now try to optimize them. It was developed by Emo Todoro's lab at Washington. So what we found is that actually this random search algorithm and linear controllers actually outperform on these Mujoko demos a variety of other approaches that were taken, including natural gradient with natural policy gradient on linear controllers, natural policy gradient with some weird nonlinear controllers, TRPO, and essentially everything we were looking at. The linear controllers themselves actually were able to get to these solutions much faster just using random search. And so in this case, you want a larger number, and we were able to get larger rewards. But even though we get larger rewards, and I apologize because there's lights here, but let's just look at this for a second. Even though we get larger rewards, this already points out something that is, I said at the beginning of the talk, and I want to say again now, is that one optimization problem probably does not capture everything we care about in control. And in particular, this is the humanoid model. This is this last one. A humanoid model is declared successful in the OpenAI gym if the reward succeeds 6,000, right? As long as you exceed 6,000 reward, you have a success. So this one has 6,000. As you can see, it's kind of weirdly hopping on a leg. It's a little hard to, I apologize that the video is a little washed out, but the dynamics at the foot are also doing something a little funny. And this one actually is the one that gets to 11,600. Again, you've got to watch the feet, because the feet dynamics are actually absolutely not what a robot. The robot would have fallen over a long time ago. So the problem here is that, at least for these models, they're too simplified to capture reality. And in particular, the way that they're modeling the contacts might not actually be accurate enough to really carry over. And moreover, it's not at all clear what the high reward means. That's not necessarily realistic gait. The other thing that's going to, oh yeah, sorry, there was one more. Right. The other thing that is that would be worth considering is because random search is faster, we can start to actually evaluate random search on more random seeds. One of the weirdest things about reinforcement learning is the way that the random seed is treated like a parameter. That's bad. And in some sense, I really feel like one thing that we all have to think about, and if I could convince anybody to work on it, would be great, is the right abstractions for how random seeds enter into machine learning. Because you want to fix the random seed for debugging. Maybe. Do you? I actually don't know. But if you fix the random seed for debugging and you start tuning hyperparameters to random seeds, you might not actually be seeing the behavior that you want. You might be tuning to random seeds. So really, you want to think about where the randomness enters and actually think of that as a random number generator that you can't control and just take it out. But we have to think about how to do that as we plug in with, this is a complex software engineering question that I don't really know how to answer. That said, we looked at it, and what we saw is that if you just tune on 3 random seeds and then take that policy and apply it to other random seeds, you get huge variance in all of these different problems. All of the different Mujoko instances in the OpenAI gym, even for random search, have incredibly high variance, meaning that tuning the parameters for a few random seeds does not necessarily mean you're going to work on another random seed. And so here, if you have 100 random seeds for the walker, the median performance looks much different if you look at 100 random seeds than if you look at 10 random seeds. It's completely different. And so this is a really tricky thing. Maybe this is another reason to move away from pure model-based methods and start to understand a little bit more about what's under the hood. And so let me propose a way forward again, away from the pure model-free. And what I'm going to say the way forward might again be to use models, maybe. And again, let's go back. I've said this word several times. Let me define model predictive control. Model predictive control is really very much like Q-learning. They're kind of the same thing. What model predictive control does is it estimates, it solves for a Q function over a time horizon h. And oftentimes, rather than learning Q, it just specifies some Q at the terminal cost. Now, what's interesting about that is the longer your time horizon, just think about it, the longer the time horizon, if all I really care about is 10 steps, and I have a time horizon for 20 steps, that Q doesn't matter too much. And if my model is pretty good, you can actually, our simulation suggests that you depend with an exponential decay on an accurate Q function. So the Q function matters less and less. And in fact, you can oftentimes just drop it and treat it as 0 at the end if you make the horizon longer. And so what you could do is you could plan on this long horizon, have some kind of model for what the terminal cost looks like, take one step, and then replan. And even if you ignore the dynamic programming, this is an incredibly sensitive thing to do. You plan for some time horizon, you take one step, and then you plan for a longer time horizon again. And what that allows you to do is at every step, you're getting feedback. And because you're getting feedback, you can correct for errors both that come from the environment and that come from the model. And so if you plan on short time horizons, feedback can allow you to correct not only disturbances, but errors in your model. And I think it would be really interesting to understand the difference between what you could do when you have a good model and what you could do when you have an approximate model. And just as an example, here is an example of what walking looks like from the Todorov lab, who designed the Mojoko simulator. This is the same humanoid. They did this in 2012. Okay, so this is well before we got excited about reinforcement learning. And with a very simple cost function, and they even show it's robust to specification of the model, they're able to, using MPC, get the robot to, well, at least lurch. And Emil has videos where you can keep making this better if you just improve your cost function. So if you iteratively refine your cost function, you can get better walking behavior. And this one is from 2013. There's the robot doing some complex tasks. I think there's an external perturbation. He gets pulled. That's not modeled, and the thing is able to stabilize itself. So what's cool about this one is this could be actually executed in real time in 2013 with no GPUs. So in some sense, for these kinds of things, we have taken many steps backwards, trying to figure out just what are the right ways to pose these problems and really understand what's unknown here and what's hard to plan. and what are the right problems, I think are actually things that we should be thinking about in machine learning. And so what I'd like to close with is this beautiful example by my colleagues in mechanical engineering, where they actually do learning, but they learn a Q function, but they learn Q function in the context of MPC. And essentially what happens here, this is a car that drives around a track, and I'll also link to the YouTube video. You've got to watch it. And the way that they learn the terminal cost function is they start with a controller that just does lane following, PID. From that gives me values for lots of different states. That actually tells me roughly how much does it cost to go from a particular state to the end. And so what I can make the Q function be is what value did I see at this state with that action? Because I have a database. And anywhere I didn't see data, I make it infinity. And if you do that, this allows you to explore using your model inside the time horizon, but get to a safe state at the end. And this car is able to essentially, after about 10 laps, it's a remote control car, and it starts to perform better than a human controller after about 10 laps. And then it starts zipping around. This is the conference room in the mechanical engineering building. Starts zipping around that room really fast after about 20. So this is really cool. It is doing machine learning. It's basically doing Q learning, but it's using a coarse model as part of the loop. And there's lots of things that are hard that they have to push on that's still worth doing. Because the other thing that's interesting, and I honestly think this is where we need tons of machine learning, is the faster that car drives, the more nonlinear the dynamics become. The tires start to slip. And so now you have to figure out, you have to learn. That's where learning really becomes important, because at that point, you don't want to skid off the track. And so there's a lot of interesting stuff to do as you push into higher and higher performance, where learning should come in. Cool. So there's so many things left to do. I have an unbounded list. This is what fit on a slide. I want to just have some time, so let me just at least highlight these. Theory questions. Are the results that we got for course ID control for LQR optimal with respect to the parameters? With respect to the problem instance parameters? Can we actually get tight upper and lower bounds for these problems? Can we get tight upper and lower bounds in what's called the adaptive setting? We've been looking, so for people who work in reinforcement learning, we've been looking at episodic reinforcement learning. We're allowed to restart the problem. Can you work in the adaptive setting where you just get one trial? There's actually a ton of work on this. If I had more time, I could do a huge survey just about adaptive control. Trying to nail that down as well would be great. And then there are a variety of other things involving safe exploration, understanding how to incorporate nonlinearity. There's just kind of an endless number of things that are left to do. And since there are so many things left to do, I guess kind of looping back to the beginning, it seems like reinforcement learning is kind of this critical problem that we really have to start tackling, right? And, I don't think that control theory itself is going to solve all the problems we want to solve with these tools. And so it seems that this is why, it's a little funny, but I figure we just need a new name. And we need a new name. I know it's tongue-in-cheek to call it actionable intelligence, but we need a new name because I think this has to be an inclusive effort. It can't just be deep reinforcement learning. It has to take into account things from controls engineering. And actually, I think what's also interesting is I think it has to take into account something even broader. Because even the most mundane machine learning systems start to look like RL systems if you squint at them. So consider recommendation. Recommendation was something I worked on decades ago. It seemed like it was a fun problem. It was a very innocuous problem. Who wouldn't want to just be recommended some movies to watch on the weekend? Or like the next heavy metal song that you really want to hear, given the long day at ICML. But what we started to observe is that these recommendation systems, when put into feedback with people, start to make people do things that maybe aren't great. They start to bring out the worst of us. And in particular, we know that maximizing engagement is the easiest way to do that is to make people angry. We know that YouTube provides all sorts of radicalizing behavior by just feeding people more and more stuff to keep them addicted to the site. And the reason why that happens is because we keep retraining the model to maximize these metrics, which maybe aren't the right metrics to maximize. So if we don't know how to build a cost function for walking, we definitely don't know how to build a cost function for people are getting valuable time out of products. So instead, we just use time. And when we do that, basically, that's reinforcement learning now. It feels like it's supervised learning, matrix completion, but if you keep retraining, you're doing machine learning with feedback, and now it's RL, or maybe perhaps we're going to call it actionable intelligence. And so I think the future here, it's like all of machine learning has actually become reinforcement learning since we started putting everything in production. In interfaces with humans, it's going to be at the forefront of all of kind of our infrastructure. And so it's imperative for all of us, we all have to start thinking about what's the right way to do this safely, what's the right way to do this reliably, and what's the right way to do this in something that will be predictable without human intervention. And I think that's exciting. So I think, I challenge everybody here. Let's join in on this effort. It's certainly more fun than just thinking about least squares. And so the theory questions are wonderful. The outcome couldn't be more important, and I'm looking forward to collaborating with everybody on this. So thanks for your time. We do have time for questions. You have to go to the microphone, I was told, while people go decide if they want to ask questions. I do want to thank Sarah, Aurelia, Horia, Nick, Max, and Steven for kind of working with me on the problems that we had here. And there's a huge list of acknowledgments, if I had more time, of other people I'd like to thank who helped put this together. Please.
How does the model predictive control work on the quadrotor example you were showing?
The simple LQR problem?
Yeah.
It works great because you could just truncate the time horizon. So just having it, you don't even have to model the Q function to get that to work.
Thanks.
We can't take questions from next door.
Thank you
Go
for
ahead.
the nice tutorial. I have a general question. You mentioned in your talk that a lot of RL work is difficult to reproduce, and we definitely see that as well. So I guess I have two questions. First, as a researcher, what should we do if someone has a fabulous result but I can't reproduce? Second question is, as a community, what should we do? Thank you.
That's a great question. I think it's one we definitely have to grapple with. Joël Pinot actually sponsored kind of a reproducibility challenge. And it would be kind of crazy if we could scale that out. We have a lot of resources because of sponsors who have a lot of cloud computing. I think it's expensive to try to have the community have everything be replicated, but if we could try to think about ways to have all of these experimental results subject to some kind of replication, I think that would be really fantastic. I guess the one thing I want to point out that's interesting to me is that for machine learning, I actually think that the standard old machine learning, I feel like reproducibility has gotten much, much better than any time I've ever experienced it. Everybody puts things on GitHub. More or less, GitHub returns what you want. Maybe it's not exactly what people told us it did, but for supervised learning, if an idea is good, it gets reproduced super quickly. The example I have in mind is this transformer network for translation, which appeared on, before even the code was released. This is crazy, because this never used to happen. Before even the code was released, people had prototypes that seemed to work pretty well. And so that idea caught on. And it could just very well be that RL isn't at that stage yet, and we need some more mature thought about algorithms so that we can get to that point where someone could state an algorithm in a paper, and we could all reproduce it at home. And I feel like in some sense, that's the bar we want to get to. Go ahead, Ryan. Go ahead.
Okay, yeah, that was a really amazing tutorial. Thank you. I just wanted to ask quickly
No,
what.
okay.
All right.
Just, you could go next. Go ahead. Oh, okay. Go announce that. Fine. Then Ryan will go. Go ahead. Make an announcement.
Oh, hi. I'm Rosemary. Yeah, I just wanted to say we do have the reproducibility workshop on Saturday. So if anybody wants to come, feel free to come. Yeah, thanks.
Awesome. So continue that conversation there. Unfortunately, I can't go, but next time. Go ahead, Ryan.
I was just going to ask, do you have any optimism about whether your end-to-end bound on course ID would work for mapping between simulated environments and real-world implementations?
Yeah, that's a great question. That's a great question. I think this is one of these hard things for machine learning, where we're so used to not having to model anything and having great results. And when the real world comes in, we do know, and we've seen, I'm always entertained by these things, that you can introduce adversarial perturbations and break machine learning systems. This has been a very hot area of research. Turns out that they don't even have to be that adversarial. If you show a video to an image detector, it will get mistakes every other frame. So I guess this is this weird thing where it's like, I don't know. Understanding how to transfer to the physical world is very complicated. I don't think we've really solved it for the vision problems. However, for robotics, for a lot of robotics, it works, right? A lot of robotics, if you model the physics well and you build a very specific simulator for the robot you're building, people have been able to use simulators as part of the design pipeline. It's definitely a mature technology. And it would be great to really understand how to do that with machine learning in the loop as well. But I think that's... I don't know enough to yet comment about what the possibility of what we need to do to make that happen.
So I just had one question too. You kind of had those C's earlier, and you said that some of the theorists were really interested in actually the C, not maybe the sample complexity bound.
Yeah.
So there's this weird tension for doing this minimization where you're trying to drive the state to 0, but that actually also means that you have less excitation. So you're actually not less excitation in like the regress or the state. So maybe you could give some comments on, that's one of the things in adaptive control we struggle with. Is like if you try to drive a system to be stable and safe, you are stealing information for the ability to identify the system. So you kind of alluded to that, but that's also kind of like a major issue. That's
right. That's exactly right. This is actually a real challenge in the adaptive setting. And this is something that is always a little bit weird in the practice of reinforcement learning, that you don't necessarily see the difference between episodic and adaptive reinforcement learning. In episodic, you get to constantly reset and constantly retry, and then you get to do a variety of different control actions. If you need to have your system be safe, and you really want to drive your system to be stable, that's antithetical to exploring to learn how to be better. And in the example I gave about cars, it does seem like if you've never, what is the right algorithm to explore going faster if you don't really know what happens if you push the accelerator down further? So you have to assume something, right? And I think this is what makes the adaptive control problem considerably harder than the non-adaptive case. So it's something to be. But this is why it's a great research problem, and there are lots of folks working at addressing exactly that. And there's a lot of great work at actually just understanding exploration, not even from the theoretical perspective, but understanding how exploration and safety interact that I've seen. In particular, there was a paper by the groups of Angela Scholig and Andreas Krause, which actually tries to estimate exactly how bad it would be to move away from things that you already know are safe, which I thought was pretty interesting. Any other questions? Awesome. I'm happy to stick around if you want to ask things one-on-one. We have 10 minutes. Thanks, everybody, for your time.